Good morning, good afternoon, wherever you may be in your day. Thank you as always for choosing to make chemistry part of your day. We're going to continue with the ideal gas law. We're going to continue with the ideal gas law mathematically and sneak in a little bit of qualitative here and there. And we're going to do that, and we're going to trickle in the idea of density and stoichiometry. So two ideas from in the way long ago of weeks past with the same mathematical relationship. As a reminder, all our volumes need to be in liters, all our temperatures need to be in Kelvin, all our amounts need to be in moles, and all our pressures need to be in atmospheres. If you need conversion factors, here they are for you. But again, there are a couple problems in the chapter where you can get away with shortcuts on units. If you want good habits, all of your blanks need to be blanks. Okay, so there's really three ways to handle these density calculations. One is do a little mathemagics. Be comfortable with algebra, and I hope that describes everyone in the room. Number two is memorize what's in the box. Oh, it's horrible. You're just having brain cells of memorizing unconnected facts. That doesn't really do you a lot of good. Or number three, I can show you a little bit of trick to make it kind of easy. Anything with density of gases, assume the volume is 1 liter. This is actually how I'm going to work the problem. Most people are probably either going to teach you the mathematical or memorize the box. This is kind of the shortcut trick that'll work for you. Let me show you the math real quick because I do like math. I like to not just tell you guys when stuff magically comes out. So we know density is mass over volume. We know PV equals nRT is the ideal gas law. And we know that we can calculate moles by taking the grams and dividing by the formula weight. Or, symbol-wise, this is mass over the formula weight. So if I, instead of N, I plug in mass over formula weight here. And now I divide both sides by the volume. Now I have mass over volume I can substitute in density. So I have the pressure of a gas equals the density of the gas times the ideal gas constant, the temperature, and the formula weight. So there's a couple things here of note to look at. Number one is that if we change the pressure, if we increase the pressure, that increases the density. They're on opposite sides of the equal sign. Again, you can do that trick where you make everything one, double this side, you better double the other. So if we increase the pressure, we increase the density. Again, don't memorize these. Think about the thought process. If we increase the temperature, then typically we decrease the density, all other things being equal. And the formula weight, the greater the formula weight, the greater the density. And this is probably the most important of those take-home messages, and this probably makes sense. Heavier things are more dense. The gas molecules, again, we assume their volume is negligible to be an ideal gas. So the only thing that really is mattering with this density, all the conditions affect the density, you make it higher or lower. But as far as comparing density of gases in the exact same room. So in the room you are in right now, every gas is occupying the same volume. Every gas is at the same temperature. They're all in the same room. So now we start to look at this. We get that temperature, and all of a sudden, and the pressure inside the room's the same. So all of a sudden, what's really dictating the density of that gas? It's just the formula weight. So if you're worried about radon poisoning, avoid the basement, avoid the bottom of the floor. That's where the radon is. Its density is 200. If you want to try to somehow find trace amounts of helium, I suppose go to the ceiling. It's going to be lighter. Its density is only got a formula weight of 4. So those things happen. Actually, the fix for radon is literally just put an air pump in and pump the air out, so that take the air out as it trickles up from the house, so that it doesn't even get in your house. So yeah, it's actually a pretty easy fix for radon. So nothing to be scared of if you have to do that remediation to a house, or if you're looking to buy a house and you get a deal because people are like freak out when they hear the word nuclear. Like, nuclear! It's a bomb! Yeah. We're going to be a little more sophisticated as learned people, as educated people after having gone through all these videos with me. Okay, enough of the math, enough of the concepts. Let's actually practice this. So, again, it's a gas problem. I want you to underline everything, put symbols. Chloroform is a common liquid used in the laboratory. Sentence doesn't matter other than to properly excite you for the problem. Now that you're all excited, it vaporizes readily. Now I'm super duper excited. I got 2 sentences of filler. That's fantastic. I'm super duper excited. Moving on. If the pressure of the chloroform vapor in a flask is 195 torr, awesome. That's a pressure. 25 Celsius, that's the temperature. The density is 1.25 grams per liter. Grams is amount, liters is volume. What's the molar mass of chloroform? P, V, N, and T. That tells me this is a PV equals nRT. It's one shot. We're just going to plug in. So what's that look like? Okay, so I remember Dr. Werger said whenever there's a density and there's not really a volume, so let's just assume the volume is 1. That's what Dr. Werger told me, and I try to listen. So we're going to assume, and this is going to make the math easy, that the volume is 1 liter. Now the rest of this is going to be pretty straightforward. Pressure we need to convert to atmospheres, so I'm just going to do this in one step. We divide by 760. Our volume is 1. Moles we're looking for. The constant is a constant. We just look it up in the back of the book. And the temperature is 25 degrees Celsius. We have to add 273 to make that Kelvin. So that's 298 Kelvin. We can solve for our moles, which seems like a good idea. And I get 0.0105 moles. And again, we've done nothing wrong. Math looks good. But have we answered the question? And the answer is no, we have not. So let's take a little bit closer what they're asking us to calculate. And I know sometimes you all get annoyed at me when I'm like, big M is what? What is it blank per blank? What are the units on formula weight? Blank per blank. There's a reason for this. If we know the molar mass or formula weight is grams per mole, then at any point for a given substance, if we can know how many grams we have and know how many moles we have experimentally, if we take the ratio of those two things, we will get our actual identity of the compound or molar mass. So in this particular case, I have my moles. We assumed 1 liter, so there's my grams. So if I want to get formula weight, I just put my grams over my moles, multiply that through so I get my 1 on the bottom that I'm used to. And I get 119.2, or I'll just call it 119. And this is a good way you can identify gases fairly straightforward this way. You can, this is not hard data to collect. Pressure gauge, temperature gauge, density, you're all set. Thank you very much. Oh, we got more, sorry. We're done with this problem though. We're not in wrap-up mode yet. Okay, let's do a concept check real quick about what the ideal gas law really means. 3 identical flasks are in a room. One of them we fill with helium, one we fill with argon, one we fill with xenon, and they're all filled at room pressure, so same pressure. So my question is, which one of those has the most atoms in it? And as always, everything boils back to this. Pun intended there. Pressure is the same for all of them. Identical flask, volume's the same for all of them. We want to know about the amount. The gas constant's the same. And the temperature is the same because they're all in the same room. If the pressure, volume, and temperature are the same, then the amounts have to be the same. So all these are the same. This is a trick question. They're all the same. And what's interesting is, so in the room you're in right now, if you take 2 identical empty bottles and you cap them, you know there's the exact same number of molecules in both bottles. Now the mixture could be, you could breathe into one, and it could have a little more CO2. You could breathe out of one, I suppose, and well, that wouldn't really affect the oxygen content because the air coming back in. But you get the idea. Even if the content's not the same, if you cap 2 bottles in the same room, you know they both have the same number of molecules in them. So that's kind of interesting. It's kind of one of those odd things that falls out of the ideal gas law you might not think about. Which has the largest density? Well, this relates to formula weight. Helium's 4, argon I think is 40, xenon's 100 something. It's going to be clearly xenon because that has the largest formula weight off the periodic table. So let's heat up flask number 1. Let's cool down flask number 3. Which one's got the greatest pressure? Well, we're really not doing anything fancy here. So again, let's take this idea of everything as 1. And it really said what? If we heat, we want to know what happens when we heat the flask to the pressure. So what's more than 1? 2, great. Now I want to know what happens to the pressure. So the pressure goes up, the temperature goes up. So I want the one where it gets heated. So it's going to be the helium. And then same idea as number 3, which one has the most atoms? Ha, Dr. Werger, you're not tricking me this time. They're still sealed, still the same containers. It's still the exact same number. Still all the same. So again, just think about this mathematically, conceptually. Work some of those piston problems in the book or in the multiple choice practice I have posted online. Those are good things to look at, not just the long calculations, but some of the short concepts too as well, and the checks, and what does it all mean? You know me, I like to do the math, but I also like you to know what it means. All right, one more calculation, then we'll call it a day on this video. Pure oxygen was first prepared by heating mercury oxide, boom, boom, pouring out quicksilver, bubbling out oxygen. What volume of oxygen, as STP, is released by heating 10.57 grams of mercury oxide? So same idea, volume V, T and T, P and P, N and amount. So we got PV equals nRT, it's one shot, plug and chug. And STP stands for standard temperature and pressure, and I apologize for this, but standard temperature in this chapter is different than the last chapter. It's 273 Kelvin and 0 degrees Celsius. The pressure is 1 atmosphere. So let's take a look at this PV equals nRT. So what's my pressure? Standard pressure, so that's 1 atm. What's my volume? I don't know, that's what I'm trying to calculate, so I'm just going to leave that there as a variable. Let's come back to N. R is still R. And T is going to be standard temperature, so that's going to be 273 Kelvin. The real trick in this whole problem is how do I get the moles? This is the ideal what law? Gas law. What's my only gas up here? Oxygen. Those of you that are astute notice we were asked about oxygen given mercury oxide. This is that ding, ding, ding moment where you go, ooh, I know this one, mole-to-mole ratio, mole-to-mole ratio. And you are absolutely right. So we take the 10.57 grams of mercury oxide. We're going to divide by the formula weight and use a mole-to-mole ratio. So this is, actually in this case it's easy, it's 1 to 1. No, I'm sorry, I didn't balance my equation correctly. That's 2. 2 moles of mercury oxide per 1 mole of oxygen. And then that number would go right here. And I'm going to have to admit I forgot my periodic table. Hold on a second. Never leave home without it. Mercury is boy, I need better glasses. 208.59. I get 224. Um, 0.0235. And I get a volume of 0.527 liters, or 527 milliliters. And that would be the answer to the problem. And I want to point out one more thing you see sometimes in the literature, or in these questions or textbooks. And this is the idea of STP and what's the volume of a mole. Because with STP, the pressure is constant, the constant is a constant, the temperature is a constant. So we can actually solve for the volume of an ideal gas. So if we put in 1 mole, what would be that volume? And it becomes a conversion factor. So if you just plug in 1 for the pressure, 273.0821 for R, and you solve for the volume, what you get is a molar volume of 22.4 liters per every mole of gas at STP. Now this is nothing you'd have to memorize. Some people have you memorize, some people have you use it as a conversion factor, so I wanted to point this out. But if you just plug 1 and 273 into this, you can always solve for the volume in the moles. But this is a good idea. I do like this for a concept check. So 22.7 liters is a small beach ball. I should have brought in one that's actually the right size. That's in the office. But it's a small beach ball. And that's 1 mole of gas. So just to give you an idea when you're thinking about and conceptualizing these ideas. So that's all I have for you in this video. Thank you so much for your time, attention, fantabulousness, and have a wonderful day.